It's Pietro Monticone and Claudio Moroni. So this presentation, it will be a remote presentation. It's about, as I can see, a Julia package, MultilayerGraphs.jl. So this is quite interesting, how to handle graphs that have multiple layers. So let's listen. So the floor is yours.
Okay, so thank you very much to the organizer for having us and for the previous speakers for their insightful talks. So we are sorry we're not being able to attend there in person, but we have to meet with at least some of you in Boston at JuliaCon this July. And in particular, I would really like to thank Schufel and Kaminsky for their precious tutorials introducing the basics of Julia and the Julia Graphs ecosystem, because you've made our job much easier and our presentation quite a bit lighter. So thank you very much. Yes, we are members of the Julia Graphs organization, developers and maintainers of MultilayerGraphs.jl, which is the Julia package extending Graphs.jl for multilayer network science. We're going to present it to you today. But first, a few words about the logistics of our talk. So it will be divided into two main parts. The first one on the theoretical framework and scientific applications will be presented by me, while the second one presented by Claudio, my colleague, will be more focused on the practical computational software engineering aspects of the package and some of the issues and challenges. So furthermore, let me just say that these slides with all the relevant resources and references to dive deeper, they are fully reproducible and hosted at the GitHub page that we will link after the talk in the chat. And if necessary, we will send it, of course, to the organizers to make sure that that they're publicly available on the Institute website if necessary. Okay, so what is multilayer network science first? So why do we need to care about this theoretical architecture and build associated computational tools like MultilayerGraphs.jl itself? Well, in brief, all this is motivated by the realization that many real-world, complex, time-dependent, interconnected systems do not live in isolation. So they're not single layer, as you would like to say. So they, in fact, interact with each other and as layers of networks. So we're going to refer to those structures as multilayer networks in the future, in the rest of the talk. And they are often characterized by multiple types of connections. So let's just think about the follow, retweet, like, reply, mention networks on Twitter, or multiple modes, of course, and modalities. Like, for example, just for the human system, you might, describe it with different layers of description, from the biological to the chemical to the sociological, socio-technical, and ecological. And of course, you might even make use of different multiple spatial and temporal scales. So you may just want to describe a graph system evolving over time, where each individual layer is just one time step, right? So it must be said that multilayer network science is a very young interdisciplinary field, so probably not more than 20 years old, if I'm not mistaken. And therefore, as we might reasonably expect, it is not, yet transdisciplinary, if you would like to say, right, or unified, as we might like. So the relevant literature is rapidly growing, and sometimes with significantly different vocabularies and different linguistic conventions and modeling choices that probably, depending upon the original field and background of the author, depending upon if it comes from mathematics or computer science or physics, etc. Therefore, I really believe that it might be useful to informally sketch the overall conceptual framework by probably highlighting the nomenclature, the terminology, and kind of the conventions that we have actually implemented in the package, and that we will try to adopt as consistently as possible as we go through the talk. So when we talk about a network in general, we mean the concrete, instantiated, observable interconnected system under examination. So basically the data. And by graph instead, we actually mean, as we many talk we've seen before us, the abstract mathematical relational object, right? The pair of vertices and vertex sets and edge set that obviously we use to encode and assimilate the network data we've talked about before. By vertex, in the context of multilayer network science, is meant by as the local layer-specific instance or representation of a node. Sometimes in literature, you will find terms like replica node or state node, something like that. And of course, in MultilayerGraphs.jl, you can really add, remove nodes, vertices as you like. By node instead, we mean the global multilayer-wide equivalence class of vertices. So what sometimes in literature is called physical node. And by layer instead, obviously, we mean the standard subgraph constituting multilayer graphs. And as MultilayerGraphs.jl allows, they can be with or without self-loops, might be directed, undirected, weighted, unweighted, metadata rich, metadata poor, with value, without value, etc. By intra-layer edge, we mean just a connection or edge within a given layer. And by inter-layer edge, we just mean the edge between distinct layers. And the interlayer structure is actually the bipartite graph connecting the layers. So again, they can be directed or weighted, unweighted, metadata rich, etc. And the multilayer, when we refer to the multilayer, we will mean the overall global structure of it all. And of course, here in the chat, in the slides, you will really there are links to the direct links to the API, to the documentation. And if you really want to dive even deeper, you can find the you click to the source button and you go to the source code directly. So the concepts that we have just introduced allow us to distinguish basically 4 types of interactions. The self-interaction, which is just between a vertex and itself within a layer. The endogenous interaction, which is between distinct vertices belonging to the same layer. The exogenous one, which is between distinct vertices belonging to distinct layers and representing actually distinct nodes. And the intertwining kind of interactions, which is between distinct vertices belonging to distinct layers, but representing the actual same node. And of course, depending upon the chosen constraints, right, we can delineate a basic taxonomy with 4 main classes of multilayer graphs. And all of them are implemented in MultilayerGraphs.jl or constructible, okay, in MultilayerGraphs.jl. And there are, of course, the edge color multilayer graph, which is the one that we obtain if we admit self and endogenous interactions. The multiplex one, which is the one that we obtain if we just admit self, the endogenous and the intertwining kind of interactions. And the interdependent is the one that we obtain if we admit the self, endogenous and the exogenous one. And the general if we do not apply any constraint at all. And some of them will be shown in the tutorial by my colleague Claudio afterwards. More formally, let's begin by considering the adjacency or weight tensor representation of a standard monolayer graph we've seen in many talks before ours. Here we're going to adopt the Einstein symmetrical convention for just notation simplicity, where n is the number of vertices, WAB, little WAB is just the real non-negative scalar that represent the interaction intensity between nodes A and B in this case. The capital IJAB is just the mixed canonical rank 2 tensor, as you might probably know. And with a very similar approach, we just generalize it, defining the multilayer adjacency or weight tensor, encoding basically everything we need to know to fully concretely specify the multilayer graph of n nodes or equivalence classes of nodes of vertices and L vertices, L layers, sorry. So notice that, of course, we're using, in this case, Greek indices for layers and Latin one for nodes. Then, of course, we're just for clarity and to make it a little bit more smoother with the conceptual framework kind of slides, performed linear decomposition to underline the main types of interactions we introduced before. So that's just for simplicity. But since we want to operationalize the whole thing and make our life not too complicated for the scientific computational applications, it turns out that it's very useful to flatten, to matricize, as we will say, the multilayer adjacency tensor into the so-called super-adjacency matrix. Again, all of that, if you click the link, you can go directly to the API of the package. And of course, that we can arrange in the most convenient way, because obviously the super-adjacency matrix is not like a tensor is coordinate dependent and is not unique, right? So in the most convenient arrangement shown in the figure, you can really see that on the diagonal blocks of adjacency matrices, they encode the intralayer connectivity, and the off-diagonal one encode the intralayer ones, right? So interlayer connectivity. So very briefly here, because there is not too much time. So as I said at the beginning, MultilayerGraphs.jl extends Graphs.jl, right? And therefore, it inherits all the monolayer methods, all the metrics, all the descriptors. It includes and adds the multilayer generalization. So if we have the multilayer degree centrality, you know, this local property of the graph, we really extend to all single layers, all the interlayers, and the overall multilayer graph structure the same thing must be said by about the eigenvector centrality, the modularity, and optimization algorithms, and the von Neumann entropy that Claudio will show afterwards in the tutorial. So a little bit about application, but I have not much time. But basically, what I want to say is that multilayer graphs have been adopted to model kind of the structure and dynamics of a kind of a wide spectrum of high-dimensional, nonlinear, multi-scale, complex systems. You know, from the physical to the socio-technical, and from the epidemiological to the economic network. So, in the interest of time, just obviously cannot do full justice to this vast range of scientific fields that studied and published papers on multilayer network systems, but some relevant references have been reported in the last few slides of my part of the presentation. Instead, I've decided to focus very briefly on one specific field, which is the one of very cogent, very pertinent in these times, which is the multilayer network epidemiology. Given the recent, obviously, COVID-19 pandemic, recently probably ongoing, not sure, COVID-19 pandemic, and its policy relevance more generally for planning and preparedness. So I really would like to focus to two kind of examples, because in my view are the most comprehensive and the most clear and crystal clear examples. And basically, when you're in the field of multilayer network epidemiology, where you might want to perform tasks such as short-term individual ensemble forecasts of some specific policy relevant incidences, or individual and ensemble nowcasting projections, prospective or retrospective scenario analysis, and something like that, conditional predictions, etc. Like in these two cases that I'm showing here, you really want to take into account the different structure of the different settings in which human contacts happen, right? So, so there are basically two main points why I've chosen these two examples to kind of to talk to you about multilayer network epidemiology. Because first of all, because the underlying model, which is a very complex high-performance model with a stochastic, agent-based, age-stratified, geolocalized, that integrates demographic, economic data, etc., that is made available by, that is constructed by the MOPS lab at the Northeastern University and Network Science Institute, is fully implemented in Julia, pure Julia. That's the first reason. That's a reason that is good enough. And yes, they build synthetic populations with highly stratified contact structure. And obviously, it becomes very policy relevant to know which is the impact of different modes of interaction. So obviously, if you need to know this kind of data and integrate in your models in order to know what will be the impact of closing schools, for example. It might be very apparent the cost, but the benefits might not be as easy to assess. And so a little bit on the a very quick look at the limitations of the current version of the package and the planned future development. So basically, we don't have at the moment the functionality to import and basically we didn't extend the Graphs.jl functionality to import and export multilayer network data in various formats. We do not have at the moment a good functionality for data visualizations. We're not experts in that, and so we probably might need to develop a new package. We don't know. Probably we might use as a dependency GraphMechie or something like that. We have to add more. We have to add community detection algorithms, the multiplexity dimensions that Claudio will talk about it later, and there was another fundamental reason why I showed you these agent-based model before, because we've actually concluded the integration with Julia Dynamics ecosystem in Julia, and therefore, if you are familiar with agents.jl, the package in Julia Dynamics, they use environments, right? And among the environments where you can embed the agents, there are graph type of environments, and now you can perfectly construct and build agent-based model and calibrate and validate, etc., agent-based models that are embedded within multilayer graphs, so that you can have dynamics both on multilayer graphs and of multilayer graphs, right? for more details on the future developments, you can see the issues in our GitHub repository. I have no time to go to the related packages, but these are the Python and R related packages that try to do almost the same thing, even if the Multilayer implementation are not as general, but they're more on the visualization side in general. And these are the few references on the theoretical aspects of everything that I've talked to you about. And this is the references on the application. So now, having explored the underlying theoretical foundations and applications, scientific applications, it's kind of the time to shift our focus towards the practical implementations and implications, passing the word to my colleague, Claudio. So please, thanks.
Okay, so thank you very much, Pietro. I will try to share my screen. Just kindly ask you if you see it correctly. Yes, maybe.
Not yet.
Not yet. Okay. Yes, it's saying that my screen is loading. So now you should be seeing it. Maybe yes.
This is screen practice.
Yes.
Very well, very well. So just notice that this talk will be the last before your lunch. So I hope this will serve at least as an appetizer for you. So as Pietro correctly said, this part of the talk will be mainly concerned with the practical aspects of multi-layer graphs, MultilayerGraphs.jl. So in the first section, we will cover two technical topics that I believe have been missed in the earlier tutorials. Then we will go through the main design features of MultilayerGraphs.jl that I hope will constitute a useful piece of advice to anyone that would like to extend the package or implement a new graph package of their own. We will then see a tutorial on MultilayerGraphs.jl, and finally, if time allows, the more let's say technical future developments. So the two technical aspects I mentioned earlier are the extendability of graphs.jl and how traits are used in both graphs.jl and Julia in general. So most of the times someone wants to implement a new graph type in Julia, she or he has to implement a new graph package around it. Now this can be done in two ways. Either she or he implements a standalone package, so outside the graphs ecosystem, or it gets implemented in such a way that it extends graphs.jl. If you follow the latter route, you will have some advantages, especially two. First of all, if you extend the graphs.jl, you will be able to call graphs.jl methods on your graph type for free. And if everybody who implements a new graph package in Julia does it, we will end up, and we are ending up with an ecosystem of packages that have a very high degree of interoperability, homogeneity, and predictability for what concerns the API's name, signature, and in most cases also return types. But how does someone extend Graphs.jl? Well, you only need to overload a core set of Graphs.jl APIs that I just showed on screen. It somehow went out of Zoom, but anyway. And once you have done it, as I said, you can just call Graphs.jl method on your type. About traits, I think we won't have time to do it. Maybe an appendix at the end if you are interested. But the main point is that traits in Julia provide for the horizontal component in what would otherwise be a purely vertical type hierarchy in the Julia language. Now we turn to the main lessons that we learned by implementing MultilayerGraphs.jl that may be useful as advices for others. The first one is please when you start implementing a new graph package, maybe one should ask oneself if she or he would be better off implementing just one new graph type or an entire sub ecosystem of graph types, and the latter was clearly the case for MultilayerGraphs.jl. And how are sub ecosystems, which basically are type hierarchies, implemented in Julia? Just like I said before, so one has to combine the single inheritance with traits to have a multiple inheritance-ish in Julia. The next point is would you prefer to implement a graph wrapper, so a package whose main structs are actually wrap other graphs from other packages, or would you be better off with a full-blown ground-up implementation? There are pros and cons to these two approaches. The first approach, so the graph wrapper approach comes on top, especially at the beginning of the implementation of the package, since it is way easier to access variables, so nodes, vertices, layers, and so on. But it gets much harder when you later want to modify such variables, since graph wrapper must implement other than the field that contains the graph they wrap, also a mapping from that graph to the structure that the whole structure really is intended to represent. And so modifying modifying such structure really implies a lot of function duplication and consistency checks. So I see I only have 3 more minutes, so maybe skip the part on structure and go straight to the brief tutorial I wanted to show you. I hope it scrolls as I scroll it. No, it does not very well. So it is okay. Now it scrolls. So this will be a brief tutorial on multi-layer graphs.jl, where we will take advantage of what Pietro said before to implement a general multi-layer directed graph. We start by specifying the number of nodes. Then we create a list of nodes, and note that each node must have its unique name. I mean, you can of course create nodes that have the same name, but it will error later. Here we construct our first layer. Its underlying graph will be a simple direct graph. So this is a simplified constructor for layers whose underlying graph is a simple direct graph. It has a name, and we will later see how names are used. It doesn't represent all nodes, as Pietro said before, but only a sample of them. Yes, is there? I hear my voice. Is there a question or? Okay.
Yes, sir, Claudio, but I have a comment that we unfortunately have to leave in around 2 minutes. So if you can maybe wrap it up, that would be great. So sorry about that.
No problem. So here, all layers are constructed and put inside a list. Same for interlayers. Then you can just build the interlayer. The multi-layer graph, passing to it its list of layers and interlayers. You can access slices, both layers and interlayers, via the dot notation. And you can of course add node, vertices, edges to it, just like you would with any graph. And here are the metrics that Pietro was referencing before. I think I'm done then. There was a part on future developments that partially Pietro did, but anyway, it's on the slide, so you can look it up. And thank you very much. Then I leave you with the references to repository, paper, documentation, Twitter threads, and so on. Thank you.